we're going to go over one new topic today just to make sure we all got it on the same page. Okay? It's a fairly easy topic to go over. It's not that difficult. In fact, this is what D period. So we started talking about it yesterday. I'm just going to go over it again today, and we're going to see a kind of a picture of how it all works. Okay?
How do you pronounce that word? A-C-A-I.
I'm sorry? What?
How do you pronounce the word
Asai.
Asai?
Yeah.
Is it?
Yeah, the ACAI, yeah.
I thought it was acai.
It's a sigh?
Asai or
My
K.
sister always calls it an acai
Okay.
bowl.
Alright, So, what we're going to do again, everybody, just as a review from yesterday, we're going to look at the disk method, okay? Disk-washer method, okay? This is a way, really, okay. This is a way of generating a solid from an area, okay? So, basically, what we're going to do here is if we've got any particular area here, here's f of x, okay? Here's where we're going to start, here's where we're going to end. That's our area in question, right? Okay? Well, what this method does, okay, how we can turn this into a volume, okay, or into some sort of solid, is we're going to take this area and we're going to spin it around, okay, the x-axis, okay, like so, to form what sort of shape?
Circle.
A circle, but the whole thing would be a cylinder, okay? So the cylinder would look like, if we drew this thing out, it'd be a cylinder, it'd be cylindrical, it would look sort of vase-shaped. I'm not very good at drawing a vase. Okay. That's what this particular curve would look like there. Now it's kind of stupid, but whatever. It's a stupid looking shape. Okay, that sort of vase thing. Okay. Now, for a normal cylinder, okay, what's the volume equation for it?
Oh god, 1/3.
No. You're thinking cones.
Yeah.
Cylinder.
Pi.
It's pi r squared times height.
Pi r squared times height. Good. Okay. Right? Okay. For this solid here, formed from this area here that I spun, what is its height going to be? From, what would determine my height of this guy? Somebody tell me?
B minus A.
B minus A. So the height would be the space between A and B. So this here would represent the height, right? Okay. Now, next we would have, what would R be? What would our radius be? A little trickier, right?
It's the slope. It's the integral of f of x.
Okay, so f of x is R, right? Now why is f of x R? We're doing a circle, right?
Because that's the radius. It's just like you're taking the distance of it, which is the x value.
Okay.
And you just take
All right, well, close. Basically, here, f of x represents the radius, is because f of x, remember, is the same thing as the y, right? They're synonyms, okay? And so the radius here is going to be whatever y value you're at, okay? Now, unlike a normal cylinder, though, the solid is basically made up of a bunch of circles of varying sizes. F of x is not constant throughout. It changes, right? So this f of x right here, we'll say this is f of x sub 1, is different than the f of x right here, which is different than the one from right here, okay? Etc. as we go along here, okay? But they're all circles. So a cylinder is basically formed by taking a bunch of circles and adding them all up one on top of another. It's just that in a normal cylinder, all the circles have the same radius, okay? So they're all the same size. For this cylinder, though, that we're creating here, all of my radii are going to be different, all right? But we're still going to add them all up, okay? Well, what process do we use to add a lot of stuff up together? The integral, right? it's basically a Riemann sum. Okay, we're adding a bunch of cross sections up, except this time we're turning the cross sections into circles. Okay, and so we use the integral. So we're going to basically integrate a circle, making the radius whatever f of x is. And now, to account for the height, well, our height's from a to b. Where would we put the a and b on our integral? They would be the what?
Oh, the things.
Yeah, the limits of integration.
Yeah.
The things. The limits of integration. And so this right here is the equation for volume of a solid generated by a revolution about the x-axis. Okay? That's what that is. Because that's long to say every single time we want to say what we're doing here, we generally refer to this as the washer method. Okay? Or sorry, it's the disk method. Excuse me. Okay? And to show you what it looks like, I pulled up a nice little GIF of it, and you can see here a triangular area in question being spun around the x-axis to make a cone, right? My email is bugging. I'm getting used messages, okay? And so there you have it. That's what we're doing. And so we're forming a cone. In this picture here, you're actually forming a cone by taking that triangle and rotating it about the x-axis, okay? To get a solid revolution, okay? And you can see how the f of x is different throughout, but we're adding them all up together to make ourselves a circular cone. So everyone now, is it better to visualize what's going on here now?
Yeah.
The picture? Okay, this is the best picture I could find. Okay, on short notice. But there you have it, okay? That is what we're doing here, okay? Now, beyond the disk method, okay, we've been working with area between two curves all this time, okay? And so what we could do here is we can do the same thing, but with an area between two curves, spin around the x-axis and get a picture, okay? So if I did that, go ahead and draw our system here, okay? Here's f of x. Okay. Here's g of x. Okay. Here's my a, my b. Okay. I'm going to rotate that zone around there. Okay. It's going to basically work the same way as it did with the area, where I just do the area of one minus the area of the other. I'm going to do the volume of one minus the volume of the other. Okay. So I could write that then basically as the integral from a to b of whichever function's on top, pi, whatever function's on top, minus the integral from a to b of pi times whatever function's on the bottom. Like so. But if I wanted to, I don't have to make this two different integrals. Because the limits of integration are the same, and we're doing this with respect to x, we can actually combine this into a single integral, okay? By writing this all as actually the integral from a to b of pi times f of x squared minus g of x squared dx, okay? And this here is called the washer method. Why the washer method? What's a washer?
Thick thing.
It's a little, it's a disc with a hole in it, right? That's what a washer
nut
is.
though. It's that nut-looking bolt thing that's kind of thick.
No, that's a hex screw. A washer is like, they're small, they're thin, they got a hole in them. You put them on screws so the screw doesn't wear and destroy the screw hole.
Shut.
Okay.
I know
So,
how thick and fat.
it's there to kind of help keep things in place. Okay. That's what. But yeah, washer's just a disc with a hole in it. Okay. If it helps, think of this. Maybe call this instead the donut method. because the solids you generate are essentially going to be donuts. They're going to be these things with these holes through the center, okay? Which is exactly what a donut is. It's a fried pastry with a hole in the center, okay? Donut, okay?
All of it's done to be goodness.
Yes, like yes, you're dead. And we could use this method, by the way, to find the volume of a donut easily, okay? If we have the right equations for it, okay? But that's the washer method. Any questions about how any of this works? Pretty straightforward, right?
Yes.
Okay. Let's look at one example. Well, let's do two examples. We'll do a disk method and a washer method, okay? So with my disk method, okay, we'll find a volume, okay, of an area of a solid made by revolving f of x equals x cubed from x equals 1 to x equals 3 about the x-axis. So, we did this. Just like any area problem, we want to graph our system first. X cubed is this number here. We're doing this from 1 to 3. So 1's here, 3's way up there. So this is the thing we're going to flip around. So if I actually, if this thing was a solid, it would look like it have a flat top, very curved sides, and a flat bottom. It almost looked like the front bell of a tuba. Okay, so if you ever see like a tuba or a big horn, the bell part of it, that front, or just to chop it off and kind of fill it in, that would be the shape we would get. Okay, very much like that. Okay, so we're going to spin this around the x-axis. Okay, so the volume of this thing should be fairly straightforward. What's it going to be? How would I write the equation? Integral of what? You can look at your notes. You should have it be integral of
Or 1 to 3.
okay, hang on. So let's look at the there's the disk method. It's the integral from a to b of pi times f of x squared dx. So f of x is x cubed. 1 to 3 is my limits. Okay, so how would I write this out?
With the limit of 1 to 3
1 to 3 of
pi, and it's f of x, right?
yes, f of x squared.
So x to the 6th.
X to the 6th. You can write it as x cubed squared and then make it x to the 6th, or you can just write it as x to the 6th, doesn't matter. We'll write it as x cubed squared at first. And then we actually do it, we'll do it with the 6, okay? So that integral right there will model the volume of the system.
It'll give us the volume of the 3D.
It'll give us the volume of the 3D shape made, basically the tuba bell that we're making here, okay? We go ahead and we clean this up. Integral from 1 to 3. We can write this pi times the integral of 1 to 3 of x to the 6th dx. What's the antiderivative of x to the 6th?
X to the 7th divided by 7.
Yep.
Yeah, Chase.
From 1 to 3. So our volume then would be pi times 3 to the 7th divided by 7 minus 1 to the 7th divided by 7, which is equal to a rather large number. 3 to the 7th is not 5. Does anybody calculate? Calculators. Here's one of my calculators.
Oh. 187.
Okay. So you said it's what?
2187.
2187. Okay. So this is 2187 over 7 minus 1/7. So the full answer here would be 2186 over 7 times pi. Units cubed. Okay, so we're doing a lot of this.
Units cubed.
Okay, units cubed. Like that there. It's 2186 divided by 7, is that divisible by 7? No. Okay. So you can leave your answer like that, okay? But that's how you would do this, okay? Any questions on how to find the volume using this method? It's pretty straightforward, right? But you need to know the formula for the disk method, okay? It's not hard. It's literally pi r squared. You're replacing r with your function, okay?
That's because the function is up.
Yes, because the function serves as the radius, and we're integrating. So if you think of it, disk method, oh, that's just pi r squared. The integral of pi r squared is basically what it is, okay? You've got the disk method right there, okay? And the washer method is doing the same thing, except you're doing it with two functions, okay? So we did a quick washer method problem, okay? Like I did this one yesterday, but I'll do it again because it's a good problem. Okay? Find the volume of a solid generated by revolving the area between x and x squared about the x axis. Okay? So, again, what we want to do is we want to graph the system first. Our area in question is this sliver again. We've done this problem a few times, so we kind of know how this thing should work. Okay. Where do they cross each other? They cross at 0 and
2.
when's x equal to x squared? At 0 and at 1.
1.
Okay. That's where they cross each other, at 0 and 1. Okay. So, and x is bigger than x squared from 0 to 1. So, we would write this integral using the washer method. It'd be very straightforward. It would be the integral from 0 to 1 of pi times x squared minus x squared squared dx. So notice I did both functions the same way I did before. I normally do it, so the first one minus the second one, but I square them this time instead of just leaving them by themselves. Okay? So it's like I'm setting it up exactly like I did with the disk method, but doing it with two different functions instead of one. Okay? We work this out here, we clean this up. The pi can be factored out. The pi can always be factored out. Okay? So 0 to 1 of x squared minus x to the 4th dx. We integrate that. What's that integral, everybody? Oops. It's the integral of x squared?
X cubed over 3.
X cubed over 3 minus x to the 4th becomes
X to the 5th over 5.
x to the 5th over 5,
That's the first question.
which we do from 0 to 1. Okay? And we work that out same way we did last time. Okay? So pi times 1 cubed over 3 minus 1 to the 5th over 5. Okay? All that just minus, same thing with zeros. Okay? Which gives us pi times 1/3 minus 1/5 units cubed. Okay? 2/15 should be the answer. Okay? Pi, 2/15 pi units cubed. Okay? Is what we get when we spin that guy around. Okay? But that's what we get. That's how this thing works. Any questions?
No.
Again, it's just following a formula, and the formula is pi r squared. It's just r here is f of x squared minus g of x squared. Okay? All good? All right. So, you'll have some work to do for Saturday on getting used to the washer method and the disk method. Okay? And what we're going to do on Saturday's class, those of you who are actually here, oh, Monday's class, that's right, we don't have class on Saturday. Well, for Monday, that's even better. You'll all be here on Monday, or should all be here on Monday. We'll go over how all this works on Monday, and you'll see we'll see some of the variations on this problem. For example, we could do a disk method But instead of spinning around x, we can spin around the y-axis. That's one thing we can do. That's common. It doesn't come up that often in the AP, but it's still good to look at. What does come up more often on the AP is, instead of spinning around the x-axis, spinning around a different horizontal line, like y equals 4. Spin the volume around that, okay? Because it will change the way things can happen, okay? But that's actually not that bad, all right? Okay.